record. That's why. Okay. Okay, good. Most designs assume equal ends. Notice how I've never said there's unequal subjects in each group. I've never, ever set it up in a situation like that. Always said they're equal. Little n is the number of subjects per group, that kind of thing. Now, really simple designs, straight up one-way analysis of variance is different. So just straight up one-way analysis of variance, having unequal cell sizes is not a huge deal. Okay. It's my wife and her sister in the 1980s. All right. What if you have unequal ends? Like, it does happen. And again, if you go to the thesis conference next Friday, which for reasons that completely escape me, is at the Water Tower Inn. Well, I do know why, and I'm not going to get into it. It's not our fault, so I'm going to tell you. You should go. I won't be there. So that's another reason to go. I'll be in Albuquerque, New Mexico at a conference. No, it's not. It's not that different. That's good. Actually, it's supposed to be warmer next week, mid-20s. But most of the time, this time of year, it's not. It goes down to like -2 at night because of the desert. So you get sunburned and cold at the same time. It's going to be awesome. Okay, so, right, what happens if you have an equal ends? You'll see a lot, by the way, as I usually mention, thesis conference, you should go to support your friends, but also just to see the kind of work they do. See the kind of work you'll be doing next year. And also, you'll see a lot of people have unequal number of subjects per group. You will see that Dave's students don't. A little bit unequal is not a big deal. But what do you do if you have an unequal number of subjects? Because this is it's called analysis of variance. The bottom of a variance equation has an n in it. Oh, yeah, variance depends on the number of subjects. This is going to potentially be a problem. So what are we going to do? Well, we can estimate missing values. Suppose you could. In fact, SPSS will allow you to do this. You can tell it what to do with missing values. You can say, take the average. You can say, pick a random number between these two numbers. There's a lot of approaches you can take it, and the nice thing about them is they're all going to give you a guess that you don't know if it's right or not. So, but they'd be guesses. The mean, the median, I don't know. Depending on your numbers. Do you include interactions or not? Like, do you think to yourself, oh, should there be an interaction here or not? And I'll get to that in a second, but when you're sort of theoretically making up a number, you can't just pick a number out of the air. It's got to have rhyme or reason to why you picked it. So if you look and go, oh, well, there should be, let's see, well, any number is a linear combination of mu and alpha and beta, but what if alpha beta isn't significant? Or what if beta, oh, I don't know how to put a number there. No matter what you've done, you've lost degrees of freedom too, right? Because if you set another number, you've lost a degree of freedom. So if I tell you that, oh, I made that final number up, it's a 7, you've lost a degree of freedom because you've assigned it arbitrarily. So you can't just say, I'm going to make up 20 new numbers, and now I have enough data to find a significant effect. I saw that somebody try that once. They submitted an article to a journal. I can't believe it even got as far as getting to reviewers. Because you would think that the editor would go, yeah, you can't do that. And I knew the editor. He was down the hall from me. But I was a postdoc. And I went to his office and I said, Dave, because his name also was Dave, why did you give me this pile of garbage? They made up data, they freely admit it, and they don't take off degrees of freedom. And he said, I did that because I knew you would find it. I said, well, you found it. Anyway, whatever. But it was shocking. It's like, you can't just make up numbers. You can't say, well, here's some more numbers. They're in our equation. We win. It doesn't work like that. I don't know who that dumb guy was there I was doing, but I think it was that researcher. So what do you do? There's other ways you can do this. most of our analyses, this starts to get weird. Uses what are called type 1 sums of squares. And type 1 sums of squares are, in fact, the formulas I've been showing you. You know, sum of the x minus x bar. So let's go with, I don't know, let's do, so sum of the column means minus the grand mean divided by squared divided by the number of columns minus 1. Take the square root of that, blah, blah, blah. Or not the square root, like that. That'll give you your mean square, yay. Those ones with the summation signs, those are called type 1 sums of squares. We teach those to you guys because they're the easiest thing to understand. The idea they're deviations from a mean, and they're fine if the ends are equal. Think about this. They all have little n on the bottom. They don't say little n for group 1, little n for group 2, little n for group 3. They just have little n, which means they are assuming all the number of observations the same in each cell. But when they're unequal, those formulas fall apart. And you're like, what? What do you mean they fall apart? Well, first of all, if you did any of your stats assignments, instead of doing them with SPSS, you did them by hand, I made sure there were equal numbers of cells, equal number of observations in each group. So if you did them by hand and used type 1 sums of squares that I taught you, it worked out just fine. If I had different numbers of cells per group, you might go, well, what do I put in for n? That's why I don't do it. There's a weird thing about type 1 sums of squares. They're good. They work fine if there's an interaction. Okay? But the order, and the order if you test A first rather than B first, it doesn't matter. That's good. We don't want that. That shouldn't happen. Okay. So there's got to be other kinds of sums of squares. So let's look at some of these other ones to see what happens. Because these fall apart when they're unequal. They don't work. Well, there must be another kind. It must be type 2 sums of squares. I don't know the formulas for type 2 sums of squares. Do I? They're all matrix algebra. They're good when there's a missing value. These are great. Hey, we've got something with a missing value with unequal cell sizes. Excellent. Awesome. Okay, so these somehow, through mathematical wizardry, take advantage of this, and some mathematical wizardry take advantage of the fact that we can now have unequal or missing values. Unequal cell sizes or missing values. Except if there's an interaction. They don't work very well if there's an interaction. And you're putting out empty cells. Or not empty cells, but missing values. I'm not going to get into the mathematical esotericness. I don't even know what the word is. That's how much I'm not going to get into it. So that's not great. It's okay. What about type 3? Of course there's more. Type 3 sums of squares. By the way, these are the ones that your SPSS uses type 3 sums of squares. PSYC uses type 3 sums of squares. The nice thing about type 3 sums of squares is they're the same as type 1s if the number of subjects is the same. So if the number of observations is the same, so like 20 subjects per group, type 3s equal type 1s. So if you don't know if there's interaction or not, you use type 3s, because they're the safest one. So we teach you, when I say we, statistics professors, teach you type 1 analyses. And you don't really run into type 3s as, why are we doing this? Until usually it's more of a graduate school kind of topic. Because you need a lot more mathematical background to get it. A note there. It's funny, sometimes I look at because I've got presenter notes, and my presenter note there just says yay. So I guess I'm supposed to get excited by this. Hey! So if n's are equal, by the way, type 1 equals type 2 equals type 3. So we use type 3 in our analyses, but we teach you type 1s. We do that because this is matrix algebra that is beyond your mathematical ability for most of you. Right? You just don't have the background. The difference is when you get to graduate school, a lot of times what they'll do is say, oh, do you need to do matrix algebra in school? And you'll go, no. And your prof will go, well, you should learn it for next week. It's just expect a lot more of you, is all. I still have trouble with matrix algebra. Okay, so type 3s are great.
Oh, yeah.
I'm going to show you, so this is analysis. This is actually from PSPP, I think. I don't think this is from SPSS. I just put some data together, and I put some missing cells in. So you can take a look at some of these. This is type 3, type 2, type 1. Notice how it says A, B, given A. So the order you actually put them in the order you enter them in the table affects the analysis, which is, I know, a strange thing. Take a look at this. These are pretty similar. These are pretty similar. Oh, the interactions are exactly the same each time, which is nice. Okay. What else do we have? The error changes. No, the error is the same size all the way through. Right? So the mean square for error is always the same. The F's are just subtly different. So this is a case where we have different numbers of subjects per group, and that's why this comes out this way. And you would not get these, you can get these outputs if you go into the options and check them. No one ever does it. Just stick with type 3. If you look at your analysis, it'll actually, in SPSS, it'll actually say type 3 sums of squares. So this just shows you that there are differences between the analyses. Right? Like type 3 is the one we stick with. Now, oh, there's another one. There's one more. This is the only kind. I don't think there's a type 5. No one's told me about a type 5. I've not read anything about a type 5. I think there's only 4 kinds. Type 4s are weird because they can work with empty cells. So what do I mean by empty cells? Like, so literally, there are no observations in like A2, B2, that kind of thing. Literally no observations. So what do you do then? Well, you can actually use type 4 sums of squares. And type 4 sums of squares come up with a solution. However, the solution is not unique. There is an infinite number of possible numbers that can go in there, aren't there? Because think about this, and I don't want to do that mathematically because that's ridiculous. Let's just do this logically. So these are going to be cell means, right? What goes there? First blush, you think, oh, 4. It looks like a 4 should go there because it would look symmetrical. Why shouldn't it be 8 million? What if it's 8 million? Could be what? Yeah. Not that bad. 8 million and 2, 8 million and 4, 8 million and 8, 8 million and 8 divided by 4 is 2 million and 2. It's easy. So the gram means 2 million and 2. But what if it's negative 6? Or maybe it's pi. We don't know. We can't know. So type 4 sums of squares actually come up with a solution, but their solution is not unique. And the thing about type 4 is, remember I said the order you do things? You can actually do type 4 analyses twice and get different results both times. Which is kind of weird, right? Because if it tests the A effect first, you get different results than if it tests the B effect first. I know that seems really strange, but it's true. I'm not making that up. What goes here? I don't know. I just don't know. You know what my solution to this is? Don't ever do this. The solution to having empty cells is don't have them. Collect more data. So, let's say it's 10 people per group. So there's 10 people here, 10 people here, 10 people here. Go find 10 more people, for Christ's sakes. Just go get some more people. Or do a one-way ANOVA. We got 3 groups, do a one-way ANOVA. Do it that way. And then at the thesis conference, when I go, why is there an empty cell? You'll say, well, I ran out of time. Just don't do this and everything will be fine. By the way, well, the thing about unequal cell sizes, not everybody's going to worry about that. I will tell you that none of us is going to say, empty cells are fine. No one's going to say that. I talk about this more as almost a sort of a statistical anomaly rather than something about research design, because this isn't something we would do. Right? Just don't do this. That's my conclusion to this. Don't ever do it, and everything will be fine. If you have empty cells, it causes problems. Try even not to have unequal cell sizes. That's not so bad because type 3s take care of that, but it's easiest if they don't have unequal cells. It makes everything easier to understand. And it makes for sure you can say, okay, I know this isn't being affected by the number of observations. Okay. Hard to believe as it may seem, we are finished with analysis of variance. I know we started sometime in the late 1990s. We're actually done with a no. You now know more about analysis of variance than everybody in the department, except for me and Paul. Probably Dwayne. Yeah, and Dwayne. You literally, I'm not kidding. Like, there's weird enough Latin squares, people know they exist, they know how to analyze them. Don't be too proud of that. That's not something to be too excited about. It's like being the fastest runner on your street. It's not that impressive. All right, questions on this stuff? Like I said, the take-home message here with this, don't do it. With Latin squares, they're fine, but you're likely never going to run into it. With empty cells, just don't have them. All right. Okay, so next time we'll start talking about, do you believe this? We're going to start talking about correlation and regression next time. Thanks, everybody.